Welcome back to Networking Basics, and we are still talking about the TCP/IP reference model and the common network protocols. I want to go back and finish up with the last three WAN protocols before we go into some other parts of the discussion of the reading material. I was just trying to finish up with frame relay and Sonnet and ATM before the video cameras shut off, so I want to get those back into the mix here. Frame relay is a protocol used with leased lines to support needs support speeds, I should say, up to 1.544 megabits per second. Frame relay connections use what's known as a virtual circuit, has a particular name called a PVC, a private virtual circuit, to establish connections with. Once established, the connections use a low overhead amount of bandwidth and do not provide error correction. You can have a frame relay compatible router to use to connect to a LAN with, and this is often quite helpful too. Frame relay lines are available ranging in speeds from 56 kilobits per second to 1.544 megabits per second and vary proportionally in their cost. One advantage of frame relay is that bandwidth is available on demand. You can install a line at 56K and later upgrade it to a higher speed by ordering the service from the carrier, usually without even having to replace equipment. Sonnet is the next WAN technology, and that's synchronous optical network. Sonnet, S-O-N-E-T. It's also a leased line system. It uses fiber optic media, though, to support data speeds up to 2.4 gigabits per second. Sonnet services are sold based on what is known as optical carrier levels, or OC levels. And they have multiples of OC1 speed, like 51.84 megabits per second. So you use that those OC lines have their units based on that OC1 to begin with, and it goes all the way up to even further than OC48, which you see in the graphic chart in the reading material. It'll go all the way, it'll go farther than OC48, but the most commonly used optical carrier lines are 1 and 3, OC1 and OC3. Then you have ATM. ATM is asynchronous transfer mode. It is a high-speed packet switching technology, and it supports speeds up to 622 megabits per second. ATM can be used concurrently with T1 and T3 lines, FIDI, Sonnet, OC1, and OC3 lines. ATM uses a technology called cell switching, and the data is sent in these 53-byte cells, packet-sized cells, and because these packets are small and uniform in size, they can be quickly routed through hardwired switches. Now we want to go into transport level protocols, UDP and TCP, a little more in detail and talk about some things to do with the packets themselves and how they are formatted, and then touch on IP addressing. The transport layer of the TCP/IP protocol consists of UDP and TCP. We've already mentioned this. Now, the user datagram protocol applications involve themselves with TFTP, Trivial File Transfer Protocol, and Remote Procedure Call, RPC. UDP accepts information from the application layer and adds what's known as a source port, a destination port, a UDP links, and a UDP checksum. The resulting packet is called the UDP datagram. It's the simplest of all the packets. The total header of a UDP datagram is 8 bytes. So whatever's in a byte, which is 8 bits, that's 8 times 8, you got 64 bits. UDP passes the UDP packet to the IP protocol. The IP protocol adds its header to the packet and then passes the packet to the LLC. The LLC generates a 802.2 frame, the LLC frame, and passes the LLC frame to the medium access control layer, the MAC layer, which adds its own header and transfers the frame to the physical layer for transmission. And you'll see a nifty little chart in the reading material. This shows you how this packet is built under UDP. When you go on to the next discussion about TCP, Transmission Control Protocol, this is a very reliable delivery of information, but the packet is much more complex. It's much more involved in it. If you look at the reading material, it says that in TCP, before the data is transmitted to the destination, a connection must be established before the information is transmitted. TCP assigns a sequence number to each packet. The receiving end checks the sequence number of all the packets to ensure that they have been received. When the receiving end gets the packet, it responds to the destination by acknowledging the next sequence number. It's like counting. If the sending node does not receive an acknowledgement within a given period of time, it retransmits the previous packet. The following, when you look in your reading material, it'll show again how this is set up and how it works. TCP adds a 20-byte header and passes it to IP. IP adds its header and passes it to the NIC card. The NIC adds the MAC header, the MAC header, to the information and transmit the packet. Well, again, it's a little more involved simply because it has to establish the connection first before the communication even starts. You'll see that when you look at these packet formats and how they are presented in the reading material, you can see that I have each of these there in the different, and it's just a symbolic representation of what the digital signaling looks like. You have the sequence number and the ACK sequence number, the header length, the flag bits, and so forth. These are some other kinds of things that are involved with the transmission of the packet. But when you look at the big picture, the TCP packet format, it does look rather complex. The first 16 bits are the source port. And then the second 16 bits have to do with the destination port. And then in the center, you see the sequence number and the acknowledgement number in the TCP packet format. We'll also find out about something called port numbers. We need to mention that. And port numbers is a port number is a logical channel in a communication system. The TCP and UDP uses port numbers to demultiplex messages to an application. Each application program has a unique port number associated with it. TCP/IP port numbers are the commonly assigned ones are between 1 and 1023, and they are the well-known ports, and these numbers are reserved for the special applications by the IA, the Internet Authority. You can see a little chart with some of them listed. This is by no means all of them. For example, you have SMTP, which uses port 25, and you have Telnet that uses port 23, and you have FTP, which uses port 21. HTTP uses port 80, for example. There are many of them, and like I say, the port numbers range between 1 and 1023. Now we have internet level protocols, IP and ARP, Address Resolution Protocol, and reverse ARP, RARP, which is Reverse Address Resolution Protocol, and then ICMP, Internet Control Message Protocol. These are all operating in the network layer where the IP protocol is active, and the function of IP, the Internet Protocol, is packet delivery with unreliable and connectionless service. When you look at these Internet datagrams, they are also called IP datagrams, by the way. All TCP, UDP, ICMP, and ARP data are transmitted as IP datagrams. You can look maybe at the reading material and you'll see the IP datagram packet format. You'll see that toward the bottom of it is the source IP address, which is 32 bits long, and the destination IP address, which is 32 bits long as well. It always begins, the IP datagram packet begins with the IP version number, and there's 4 bits of space there. It's currently IP version 4 and soon to be IP version 6. The header length, the type of service, the identification and the fragment offset, along with the flags, time to live, and the protocol, as well as the header checksum. All of these things are also mentioned in the reading material so that you can get some idea of what those mean and what those are about. Time to live, for example, is the field that indicates the amount of time in seconds that a datagram may remain on the network before it is discarded. But we have to get rid of some of this digital signaling, or else we're going to just have all of this congestion on our network. This value, 32 or 64, for example, in time to live, is set by the sender and is decremented by 1 every time a router handles the datagram. If this field has decremented all the way down to 0, the datagram is then thrown away. The protocol type is the number in this field identifies the high-level protocol that's generating the diagram and allows the destination IP to pass the datagram on to the required protocol. So ICMP is 1, UDP is 17, and TCP is 6. And then you have, of course, information regarding all the other parts of this packet. Remember that ICMP messaging has one of the most important ones is ping, P-I-N-G, and this is the way in which you can test to see if there is communication between your system and another system, to see if it is alive, if it's listening. So that's an example of an ICMP message. ARP is an interior. There must be a way to find out about the physical addresses of the hosts that are connected to the local networks. And the gateway must record both the IP address and its physical address in order to communicate. If the gateway does not have the physical address of the host to where it needs to send this information, it will send what is called an ARP packet, an Address Resolution Protocol packet, to get the host's physical address. The host will respond through what's called reverse ARP. And you can see again we have the ARP packet format, where it again is 16 bits wide, and you'll see that it has opcodes which are listed there. The ARP request code is number 1, the ARP response code is number 2, the reverse ARP request code is 3, and the reverse ARP response code is 4. Now you'll see that the sender's hardware address is 48 bits in length, which is the way it actually is in MAC addresses. And the sender IP address, since it's IP version 4, it's 32 bits in length. So you have a way for machines to be able to associate IP addresses to physical addresses so that you can get actually to a physical machine. So ARP is used by the interior gateway to access the physical address of the target machine on the same network from the IP address of the network. As we go further here, we see that there's something called hardware address length, HELN in bytes, and PLEN length of IP address. Some other things is the maximum transfer unit. MTU is the largest frame length it is possible to send on a given physical medium. There is a limit to the frame size. You can't just send anything you want to. 802.3's maximum frame size is 1500 bytes. If the datagram is larger than the MTU, the maximum transfer unit, the datagram is fragmented into several frames, each less than the MTU, which is 1500 bytes. So you can see that this is a way to manage delivery of packets, and they can't be just any size. Otherwise, it will be impossible for us to manage the network well, and will become very congested. Now, IP version 4 addressing is going to be the topic of the next lecture, and I hope you're prepared to look at some mathematics. So thank you for listening, and see you again soon.